Okay, now we're recording last page of the 3.4 notes. Let me go and clear these drawings from the previous example. Now, just so you know, you could actually model the motion for example 4 in your calculator using all these features here. And you would have to type in like these values. I suppose you would do x equals -3. Not sure why you would do that actually. We could probably do that as a class when we meet again on Tuesday, because I need to actually understand this a little better. Let's just go to example 5 because I want to get this over with. So anyway, a manufacturer produces action math man figures. The cost of producing X figures is C equals F of X dollars. Okay. What are the units of the derivative F prime of X? Well, the things that you're taking the derivative with respect to X, and X represents number of figures. So it's not time, mind you. So you're taking the derivative of F of X. So it's going to be D, or you could just say it's just going to be F prime of X. But what's going to happen here, it's going to be dollars per figure. Those will be your units. And what it means is this, it's going to be the dollar change for let me word this better. It's going to be a dollar change per for an increase of one figure. So every time you increase your figure by 1, it's going to be the dollar change associated with that. So in this case here, what this means is that if you produce 5,000 figures, the cost per figure is 14 cents. And so that's what it's a change for every increase of one figure. So every time you make one figure, it's going to be the dollar change for a dollar cost. And what do you think is bigger, F prime of 10 or F prime of 10,000? It's hard to tell, but typically the more you manufacture, the cost per item goes down. And that's because you have like these fixed costs that are associated with running a factory, and those fixed costs come more spread out as you produce more and more items. So that's one way to think about it. So in the same way we have given a special name for derivative of the position function, respect to time, which we called velocity. Economists call the derivative of a cost function or revenue the marginal cost or marginal revenue. Those that do like business calculus classes will see that often. We don't really talk much about in this course, but just want to make sure I made a mention of it. Nothing really too big of a deal, nothing I'm really going to assess, but just feel like I should bring it up. But this one I do kind of care about these two examples because they're more AP style problems. So estimate derivative from a table of values. Sometimes we're not given a function explicitly, but just select the values in the table and we're asked to come up with an approximation for the derivative at a particular value. So let's look at this one from the 2001 AP Calculus AB free response. So you're given a bunch of time values and days and the temperature in W, I suppose. And they say that the temperature in degrees of the water, so it's water, that's why I use W, is a differential function. So this differential means continuous. And at 0, the temperature is 20. And then these are the temperature values like that. The table above shows the water temperature is recorded every 3 days over a 15-day period. Okay. So use the data from the table to come up with approximate W prime of 12 to show the computation that led to the answer. Well, 12 is not shown here. Actually, no, 12 is shown here. But what you probably would want to do, because you were trying to find the slope of the tangent line at 12. So this is like 3, 6, 9, 12, 15. Trying to find the slope of that tangent line. What you probably could do is probably find the slope that passes those 2 points. So what if I find the secant line between 9 and 15? Because 12 is right in between them, right? So W15 minus W9 over 15 minus 9. So that's 21 minus 24 over 15 minus 9. Or negative 3 over 6. So it's negative 1/2 degrees Celsius per day. So even though we don't have a function to work with, and we can't take a derivative of something, you can estimate by using a secant line where 12 is in between the two endpoints here. So that's how you can do an estimation. Let's see this one more time. This is from the 2003 exam. They're looking at the rate of fuel consumption versus time. And the rate of fuel consumption is given in gallons per minute. Recorded during an airplane flight is given by a twice differential function. The reason I'm saying twice differentiable is because we might have to wind up doing a second derivative. And it's strictly increasing, okay? The graph of R and table select values are shown. So this is, again, R is the rate of fuel consumption. This is time. And use the data to find an approximation for R prime of 5. Show the conjugate least chance to indicate units of measure. So what's happening is that R is already a derivative. So that's, you can think of that as a derivative of just fuel, right? So R prime of T is kind of like a second derivative. That's what I said twice differential, in case you're curious. But regardless, 45 is in between 40 and 50 here. So I'll do a secant line. So I'll do so R prime 45 is approximately R 50 minus R 40 over 50 minus 40. And that's just going to be 55 minus 40 over 10, 15 over 10. You get 1.5, and it's going to be gallons per minute squared, because you're dividing gallons per minute over minutes. By the way, on the AP exam, I think they probably make this worth 2 points, maybe 1 point for actually having the setup and 1 point for the answer. If you leave out the units, that you have 1.5, you will get nothing for your answer. You get 1 point for your work, but nothing for that because you have to put the units. So they don't do half points or marginal points in the AP exam. You really have to be mindful that you pay attention to the directions there. So that covers the end of page 6. And I'll see you guys on Tuesday unless you're volunteering at a polling location or you're taking some time out to vote. All right, have a great weekend and we'll talk soon.